It shouldn't be alive. At nearly 3 times Earth's distance from the Sun, this interstellar comet is spraying water into space like a fire hose, 40 kilograms every second. No comet has ever done this before. Scientists say it defies every rule in physics. And what it's doing right now changes everything. This is 3I at LS, and its behavior is breaking every rule in the cosmic playbook. While you've been living your daily life on Earth, this ancient wanderer has been screaming its chemical secrets into the void, at a distance where silence should reign supreme. The discovery is so profound, so fundamentally challenging to our understanding of physics and planetary formation, that it's forcing scientists to question decades of established theory. Picture this. You're standing in your backyard on a winter night, and suddenly ice cubes start melting in your freezer, while it's still plugged in and running at full power. That's essentially what's happening with 3I at LS. Except the freezer is the vacuum of space, and the distance from our Sun is nearly 3 times farther than Earth's orbit. At 2.9 astronomical units away, this interstellar visitor is spraying 40 kilograms of water into space every single second. To put that in perspective, imagine a fire hose running at maximum capacity, the kind firefighters use to battle raging infernos. Now imagine that hose has been running continuously, day and night, for months. That's the scale of water loss we're witnessing from an object that by all known laws of physics should be frozen solid and completely inactive. But here's where the story becomes even more extraordinary. This isn't just any cosmic object acting strangely. This is only the 3rd interstellar visitor we've ever detected passing through our solar system. Think about that for a moment. In all of human history, with all our telescopes and detection systems, we've only identified 3 objects that originated from other star systems and wandered into our cosmic neighborhood. The first was Oumuamua in 2017, a mysterious cigar-shaped object that baffled scientists with its unusual acceleration and complete lack of visible tail or coma. It was dry, silent, and puzzling. The second was Borisov in 2019, which behaved more like traditional comets but carried unusual chemical signatures, particularly rich concentrations of carbon monoxide that told stories of alien solar system chemistry. Now comes 3I at LS, and it's rewriting the rulebook entirely. Unlike its predecessors, this cosmic messenger is actively communicating through chemistry, broadcasting its molecular signature across space in ways that challenge our fundamental understanding of how comets behave. It's as if the universe is sending us increasingly complex messages, each interstellar visitor teaching us something new about the diversity of planetary formation and cosmic evolution. The implications stretch far beyond simple scientific curiosity. When Dennis Bodowitz, a physics professor at Auburn University, detected the faint ultraviolet echo of hydroxyl gas streaming from 3I at LS, he realized something profound. When we detect water from an interstellar comet, we're reading a note from another planetary system. It tells us that the ingredients for life's chemistry are not unique to our own. A note from another planetary system. Let that sink in for a moment. We're not just observing a chunk of ice and rock. We're receiving a chemical message from a world that formed around a different star, in a different part of the galaxy, billions of years ago. This water, now streaming into space as hydroxyl radicals, once existed in the frigid outer reaches of an alien solar system, possibly witnessing the birth and death of planets we'll never see. But the mystery deepens when you consider the timing and location of this discovery. NASA's Neil Gehrels Swift Observatory detected this water signature in July and August 2025, using dozens of carefully stacked 3-minute exposures to tease out the delicate ultraviolet signal. The precision required was extraordinary, like trying to hear a whisper in a thunderstorm or spotting a candle flame from across a city. What makes this discovery so unsettling to established science is the distance factor. Comets from our own solar system don't start shedding water until they get much closer to the Sun, typically within 2 astronomical units. The heating from solar radiation gradually warms the surface ice, causing sublimation, the direct transition from solid to gas. It's a predictable, well-understood process that follows the inverse square law of radiation. 3I at LS is obliterating those expectations. At 2.9 astronomical units, it should be frozen solid, dormant, showing no signs of activity whatsoever. Yet here it is, spraying water at a rate that suggests at least 8% of its surface is actively venting material into space. Compare that to typical comets from our solar system, which show only 3% to 5% surface activity, even when they're much closer to the Sun. Something is fundamentally different about this interstellar visitor, and that difference is forcing us to reconsider everything we thought we knew about comet behavior, planetary formation, and the distribution of water, the most precious molecule for life as we know it throughout the galaxy. The cosmic implications are staggering. If 3I at LS can maintain this level of water activity at such distances, what does that tell us about the composition and internal structure of objects from other star systems? What conditions existed in its birth solar system that created such behavior? And perhaps most intriguingly, what else might be out there, traveling between the stars, carrying chemical stories from worlds we can barely imagine? This is more than a scientific discovery. It's a revelation that the universe is far more diverse, far more active, and far more mysterious than we ever dared to imagine. And we're just beginning to decode the message that 3I at LS is streaming across space, one molecule of water at a time. To understand the true magnitude of what we're witnessing with 3I at LS, you need to grasp just how rare and precious interstellar visitors actually are. In the vast cosmic ocean that surrounds our solar system, these objects are like messages in bottles drifting across inconceivable distances to reach our shores. And 3I at LS isn't just any message, it's potentially the most revealing communication we've ever received from deep space. Imagine the journey this cosmic traveler has undertaken, born in the outer reaches of an alien solar system, possibly billions of years before our own sun even formed. 3I at LS has been wandering through the galactic wilderness, crossing light years of empty space, surviving encounters with cosmic radiation, gravitational perturbations from passing stars, and the slow decay of time itself. The fact that it arrived here now in this moment of human technological capability borders on the miraculous. The statistics alone are mind-bending. 3I at LS is traveling through our solar system at speeds exceeding 130,000 miles per hour. To put that in human terms, if you could travel at that speed, you could circle the entire Earth in just over 11 minutes. You could reach the moon in less than 2 hours. It's a velocity so extreme that it immediately identifies the object as not belonging to our solar system, because nothing bound by our sun's gravity could achieve such speeds without artificial acceleration. But speed is just one part of the story. The trajectory tells an even more compelling tale. Unlike comets native to our solar system, which follow elliptical orbits dictated by the sun's gravitational influence, 3I at LS moves in what scientists describe as an unusually flat and straight trajectory. It's not dancing around our sun in the ancient orbital ballet that characterizes local objects. Instead, it's cutting through our cosmic neighborhood like an arrow, following a path determined by forces and gravitational influences from its distant origin point. This trajectory signature is crucial for identification. When astronomers first detect an object moving through space, one of the primary ways they determine its origin is by calculating its orbital mechanics. Objects from our solar system, even those from the distant Oort cloud, will show some gravitational binding to our sun. Their paths can be traced back and forward, revealing elliptical or parabolic orbits that make sense within our solar system's dynamics. Interstellar objects follow hyperbolic trajectories, paths that enter our solar system from the void, curve slightly due to the sun's gravity, and then continue back out into deep space, never to return. It's a cosmic flyby, a brief intersection of trajectories that offers us a fleeting glimpse into the chemistry and physics of distant worlds. The rarity of such encounters cannot be overstated. Before Oumuamua in 2017, we had never definitively identified an interstellar object passing through our solar system. The mathematical models suggested they should exist. After all, stars are constantly ejecting material, and the galaxy should be filled with orphaned objects wandering between stellar systems. But detecting them required a combination of advanced technology, lucky timing, and objects large enough to reflect sufficient light for our telescopes to spot. 3I else represents a quantum leap in our interstellar object detection capabilities. Early estimates suggest it could be the largest interstellar visitor we've ever observed, with Hubble Space Telescope data indicating a maximum width of approximately 3.5 miles. That's massive compared to Oumuamua, which was estimated at only a few hundred meters in length. The size difference is crucial because larger objects retain more of their original composition, provide stronger signals for our instruments, and offer more opportunities for detailed scientific analysis. But perhaps the most astounding aspect of 3I at LS isn't its size or speed, it's its potential age. Preliminary analysis suggests this cosmic wanderer could be approximately 3 billion years older than our entire solar system. Think about that timeline for a moment. When 3I at LS first condensed from the primordial materials surrounding its birth star, our region of the galaxy was just a cloud of gas and dust. The sun hadn't formed yet. Earth didn't exist. The complex chemistry that would eventually lead to life on our planet was still just potential energy floating in the cosmic void. This ancient traveler has been wandering the galaxy for perhaps 7.6 billion years, carrying within its frozen structure the chemical signatures of a stellar system that may no longer exist. Its parent star could have died billions of years ago, leaving 3I at LS as one of the few remaining witnesses to worlds and processes that have been erased by cosmic evolution. The preservation of ancient chemistry in interstellar objects like 3I at LS offers us a unique window into galactic history. Unlike objects in our solar system, which have been repeatedly heated and chemically altered by solar radiation over 4.6 billion years, interstellar visitors have spent most of their existence in the deep freeze of space, where temperatures hover just a few degrees above absolute zero. This cosmic refrigeration effect means that 3I at LS potentially contains pristine samples of materials from the early galaxy, chemical compositions that reflect the stellar nucleosynthesis processes of ancient star systems. When we analyze the water streaming from its surface, we're not just studying H2O molecules, we're examining isotopic ratios and chemical signatures that could reveal the metallicity, stellar mass, and evolutionary history of its birth environment. The water discovery becomes even more significant when considered in this context. Water formation requires specific temperature and pressure conditions, along with the presence of hydrogen and oxygen in the right proportions. The fact that 3I at LS contains substantial water ice suggests that its origin system achieved the chemical complexity necessary for water formation, implying the possible presence of rocky planets, complex organic chemistry, and perhaps even the basic ingredients for life as we understand it. But there's another layer to this cosmic story that makes 3I at LS particularly intriguing. Its behavior pattern is completely different from our previous interstellar visitors. Oumuamua was enigmatically dry and showed unusual acceleration that some scientists attributed to outgassing we couldn't detect. Borisov was rich in carbon monoxide, but followed more predictable comet-like behavior. 3I at LS is spraying water at distances where such activity shouldn't occur, suggesting internal heating mechanisms or structural compositions that don't match our models. This diversity among interstellar visitors is telling us something profound about the universe. Rather than finding objects that conform to our solar system-based understanding of comet behavior, we're discovering that each stellar system appears to produce unique types of objects with distinct chemical signatures and physical properties. It's as if we're receiving a cosmic catalogue of different planetary formation environments, each interstellar visitor representing a different chapter in the galactic story of how stars and planets come into being. The timing of these discoveries is also remarkable. We're living in the first generation of humans capable of detecting and analyzing interstellar visitors. Just decades ago, such objects would have passed through our solar system completely unnoticed. Now, with advanced sky surveys, space-based telescopes, and sophisticated detection algorithms, we're beginning to catalog these cosmic messengers and decode their chemical stories. 3I at LS represents not just a scientific discovery, but a moment of transition in human understanding. We're moving from a solar system-centric view of planetary formation to a galactic perspective that recognizes the incredible diversity of cosmic chemistry. And this ancient traveler, spraying its water message across space, is teaching us that the universe is far more complex, far more varied, and far more generous with life's ingredients than we ever imagined. The moment scientists realized what they were seeing in the data from 3I at LS, the very foundations of comet science began to crack. 40 kilograms of water per second, streaming into space from an object that should be frozen solid. To grasp the magnitude of this phenomenon, imagine standing next to a fire truck during a major emergency, watching the massive hose unleash its full force against raging flames. Now imagine that same volume of water being ejected continuously, not for minutes or hours but for months, from an object smaller than most cities. This isn't gentle sublimation. The quiet transition from ice to vapor that we observe in typical comets. This is violent, active, relentless expulsion of material at a scale that defies every model scientists have developed over decades of comet research. The numbers are so extreme they initially seemed like instrument errors or calculation mistakes, but repeated observations and careful analysis confirmed the impossible. 3I at LS is hemorrhaging water at a rate comparable to industrial processes here on Earth. To understand why this discovery is so revolutionary, you need to appreciate the delicate physics of comet behavior. Under normal circumstances, comets are essentially dirty snowballs, chunks of ice, dust, and rocky material that have remained frozen for billions of years. They become active only when solar heating provides enough energy to sublimate surface ice directly from solid to gas, creating the characteristic tail and coma that make comets visible from Earth. This sublimation process follows predictable physical laws. The amount of energy required to convert ice to vapor depends on temperature, which in turn depends on distance from the Sun. According to the inverse square law, double the distance, and you receive only 1/4 the solar energy. At 2.9 astronomical units from the Sun, where 3I at LS was observed spraying water, the available solar energy should be completely insufficient to drive the level of activity we're witnessing. Yet here's 3I at LS, demolishing those expectations with the force of its water output. The calculation is straightforward but stunning. 40 kilograms per second equals 86,400 kilograms per day, or roughly 86 metric tons of water daily. Over the course of a year, if this rate continued, 3I at LS would lose more than 31,000 metric tons of water. For an object with a maximum width of 3.5 miles, this represents a substantial fraction of its total mass, but the raw numbers only tell part of the story. The real revelation comes when scientists consider what percentage of the comet's surface must be active to generate this level of outgassing. Traditional comets from our solar system typically show active regions covering 3% to 5% of their total surface area, even when they're much closer to the Sun and receiving significantly more solar heating. These active regions are thought to be areas where the surface coating of dust and debris has been stripped away, exposing fresh ice underneath. 3I at LS is showing activity levels suggesting that at least 8% of its surface is actively venting material. That's nearly double the typical rate. Occurring at a distance where no activity should exist at all, the implications are staggering. Either 3I at LS has a fundamentally different internal structure than solar system comets, or there are heating mechanisms at work that we don't understand. The water detection itself required extraordinary precision and dedication from the Swift Observatory team. Water molecules in space don't remain intact for long. They're quickly broken apart by ultraviolet radiation from the Sun and other sources, creating hydroxyl radicals, HAs that emit a characteristic ultraviolet signature. It's this O signature that Swift detected, but capturing it required combining dozens of 3-minute exposures, stacking more than 2 hours of ultraviolet observations with 40 minutes of visible light data. The technical challenge was immense. Imagine trying to photograph a single firefly blinking in a stadium full of floodlights, except the firefly is millions of miles away, and its light is in a wavelength your eyes can't see. That's analogous to what the Swift team accomplished. They had to filter out the overwhelming background radiation from space, account for the motion of both the observatory and the comet, and extract a signal so faint that it existed at the very edge of detectability. What makes the detection even more remarkable is that hydroxyl radicals have a very short lifetime in space. They're created when water molecules are broken apart by solar ultraviolet radiation, but they quickly react with other materials or are destroyed by further radiation. This means that the OH signal Swift detected represents only the immediate products of ongoing water sublimation. For every hydroxyl radical detected, multiple water molecules had been ejected from the comet's surface just moments before. The spectroscopic analysis revealed something else surprising. The water streaming from 3I at LS shows isotopic ratios that don't perfectly match terrestrial water or water from other solar system comets. These subtle differences in the ratio of deuterium to hydrogen, or oxygen 18 to oxygen 16, carry the chemical fingerprints of the stellar environment where 3I at LS formed. It's like analyzing the accent in a foreign language. The basic word is the same, but the pronunciation reveals the speaker's origin. These isotopic signatures suggest that 3I at LS formed in a stellar system with different metallicity and chemical evolution than our own. The star around which it originally orbited may have been more massive or metal-rich than our Sun, leading to different fusion processes and chemical abundances in the planetary disk. The water we're observing isn't just H2O, it's ancient stellar chemistry made manifest, a liquid history of nuclear processes that occurred in a distant sun billions of years ago. But perhaps the most puzzling aspect of the fire hose phenomenon is its consistency. Rather than showing the typical variation in comet outgassing, periods of high activity followed by quieter phases as different regions of the nucleus are heated by solar rotation, 3I at LS appears to maintain a remarkably steady output rate. This suggests either uniform composition across its surface or some internal mechanism that regulates the release of material. The steady nature of the outgassing has led some scientists to propose that we're not witnessing traditional surface sublimation at all. Instead, the water may be coming from internal sources, pockets of subsurface ice that are being heated by radioactive decay, tidal forces from gravitational interactions, or even chemical reactions occurring within the comet's core. These internal heating mechanisms could explain why 3I at LS can maintain such high activity levels at distances where solar heating is insufficient. Another possibility involves the comet's structure itself. Unlike the relatively solid nuclei of typical comets, 3I at LS might be what scientists call a rubble pile, a loose aggregation of smaller icy chunks held together by weak gravitational forces. As this structure slowly rotates and flexes during its journey through space, internal friction could generate enough heat to sublimate ice from within, creating a distributed network of steam vents throughout the object's interior. The fire hose analogy becomes even more apt when you consider the directionality of the water ejection. Rather than venting uniformly in all directions, spectroscopic analysis suggests that 3I at LS may be preferentially ejecting material from its sun-facing side, creating a focused stream of vapor that enhances the efficiency of mass loss. This directional outgassing could also explain some of the object's orbital characteristics and might even be affecting its trajectory through subtle rocket-like forces. What we're witnessing with 3I at LS isn't just an anomaly, it's a fundamental challenge to our understanding of how interstellar objects behave and what conditions are necessary to maintain active chemistry in the deep cold of space. The fire hose phenomenon is teaching us that the universe is far more dynamic, far more active, and far more surprising than our Earth-based models ever predicted. Every second that passes, 3I at LS continues its impossible performance, spraying another 40 kilograms of ancient water into the cosmic void, each molecule carrying the chemical memory of a stellar system that existed before our world was even a possibility. And in that relentless stream, scientists are reading the most detailed message we've ever received from the deep structure of galactic chemistry. In the summer of 2025, while most of humanity went about their daily routines, a team of scientists was conducting one of the most technically challenging observations in the history of space astronomy. NASA's Neil Gehrels Swift Observatory, originally designed to detect gamma-ray bursts, the most violent explosions in the universe, was being carefully repositioned to stare at a seemingly empty patch of space where 3I at LS was silently streaming its chemical secrets into the void. The detection of water from 3I at LS represents a triumph of human ingenuity and technological precision that borders on the miraculous. Consider the challenge: attempting to detect the faint ultraviolet glow of hydroxyl radicals from an object millions of miles away, using instruments designed for entirely different purposes, while both the observatory and the target are moving at tremendous speeds through space. It's like trying to use a telescope designed for watching distant galaxies to instead photograph a single raindrop falling in a neighboring city. Swift's ultraviolet and optical telescope wasn't originally intended for comet observations. The spacecraft was launched in 2004 as part of NASA's gamma-ray burst investigation program, designed to rapidly slew toward the most energetic explosions in the universe and capture their afterglows across multiple wavelengths. Its instruments were optimized for detecting sudden bright events lasting seconds to minutes, not the subtle, continuous emissions from distant comets. But this mismatch between design and application actually worked in the scientists' favor. Swift's ability to rapidly reposition itself and its sensitivity to ultraviolet radiation made it uniquely capable of detecting the OH signature that water leaves behind when broken apart by solar radiation. The spacecraft's agility allowed it to track 3I at LS across the sky, while its UV sensitivity could peer into wavelengths invisible to human eyes and most ground-based telescopes. The observation campaign that unfolded in July and August 2025 required meticulous planning and extraordinary patience. Unlike photographing a stationary object, tracking 3I at LS meant constantly updating the spacecraft's pointing to account for the comet's motion across the sky. Every 3-minute exposure had to be precisely timed and positioned, with the telescope's field of view centered on a point in space where calculations predicted the comet would be at that exact moment. The technical complexity multiplied when considering that hydroxyl radicals emit light at very specific ultraviolet wavelengths, particularly around 308 nanometers. This wavelength is completely absorbed by Earth's atmosphere, making space-based observations absolutely essential. Ground-based telescopes, no matter how large or sophisticated, simply cannot detect this signal because the very air above them blocks the light before it reaches their mirrors. But even from space, the signal was almost impossibly faint. The hydroxyl emissions from 3I at LS were detected at the very limits of swift sensitivity, requiring a technique called stacking to build up enough signal to distinguish it from background noise. Each individual 3-minute exposure showed virtually nothing, just the faint static of cosmic background radiation and instrumental noise. But by carefully combining dozens of these exposures, aligning them to account for the comet's motion, the team could gradually build up the accumulated photons from OH emissions until they rose above the noise threshold. The mathematics of this process are as elegant as they are complex. Every photon of ultraviolet light that reached Swift's detector carried information about the chemical processes occurring around 3I at LS. But photons arrive randomly, following quantum statistical distributions that require large sample sizes to reveal meaningful patterns. By stacking over 2 hours of ultraviolet observations, the team collected enough photons to perform reliable spectroscopic analysis and confirm the presence of hydroxyl radicals. The actual detection moment must have been extraordinary for the scientists involved. After months of preparation, weeks of observations, and days of data processing, the spectral line suddenly emerged from the noise, like a whispered message, becoming audible in a quiet room. The characteristic signature of ejecting appeared exactly where theory predicted, but at intensities that shouldn't have been possible given 3I at LS's distance from the Sun. Dennis Bodowitz, the Auburn University physicist who led the analysis, described the moment of recognition with the profound understanding that they were witnessing something unprecedented. When we detect water, or even its faint ultraviolet echo, OAJ, from an interstellar comet, we're reading a note from another planetary system. The poetic language conceals the technical achievement involved in extracting that note from the cosmic noise. The data processing required sophisticated algorithms to separate the genuine OH signal from various sources of contamination and error. Space-based observations are subject to numerous sources of false signals: cosmic ray hits on the detector, scattered light from nearby bright objects, instrumental variations due to temperature changes, and electronic noise from the spacecraft's systems. Each of these had to be identified and removed without accidentally eliminating the genuine comet signal. The team also had to account for the Doppler effect caused by 3I at LS's tremendous velocity. Moving at over 130,000 miles per hour relative to our solar system, the comet's motion shifts the wavelength of emitted light in a measurable way. This Doppler shift had to be calculated and corrected for each observation, requiring precise knowledge of the comet's trajectory and velocity vector at every moment of the observation campaign. Perhaps most remarkably, the Swift observations also captured visible light from 3I at LS, providing crucial context for interpreting the ultraviolet detections. The visible light revealed the size and brightness of the comet's coma, the cloud of dust and gas surrounding its nucleus, while the UV observations revealed the chemical composition of that material. By combining both wavelength ranges, scientists could create a three-dimensional picture of how water was being released and distributed around the comet. The visible light observations showed something unexpected. 3I at LS appeared surprisingly compact and well-defined compared to typical active comets. Rather than displaying the extended diffuse coma characteristic of heavily outgassing objects, it maintained a relatively concentrated appearance. This suggested that the water release might be more localized than initially thought, possibly emerging from specific active regions rather than uniform surface sublimation. The precision required for these observations is almost beyond comprehension. Swift had to maintain pointing accuracy to within a few arc seconds, equivalent to hitting a quarter-sized target from a distance of several miles, while both the observatory and the comet moved through space at velocities that would carry them across entire continents in minutes. The spacecraft's attitude control system worked continuously to compensate for orbital motion, solar radiation pressure, and the subtle gravitational perturbations from Earth and Moon. The success of the swift observations represents more than just technical achievement. It demonstrates the remarkable adaptability of scientific instruments and human creativity in pushing technology beyond its original design limits. Swift was never intended to study comets, yet in the hands of dedicated scientists, it became the perfect tool for detecting interstellar water signatures that ground-based telescopes couldn't observe. But perhaps the most profound aspect of Swift's revelation isn't the technical accomplishment. It's the realization that we're now capable of conducting detailed chemical analysis of objects from other star systems. Just decades ago, interstellar visitors would have passed through our solar system completely undetected. Now we can not only spot them but analyze their composition, track their behavior, and decode the chemical messages they carry from distant worlds. The data Swift collected in those summer months of 2025 will be analyzed for years to come, each spectral line and photon count revealing new details about the chemistry of distant stellar systems. But the immediate impact was clear. 3I at LS was actively venting water at a rate and distance that challenged everything scientists thought they knew about comet behavior. And that discovery was just the beginning of a mystery that would reshape our understanding of how water, life's most essential molecule, is distributed throughout the galaxy. When 3I at LS began spraying water at 2.9 astronomical units from the Sun, it didn't just surprise scientists. It shattered fundamental assumptions about how the universe works. For decades, comet science has been built on a foundation of predictable physical laws. Temperature decreases with distance from the Sun, sublimation requires specific energy thresholds, and ice remains frozen until sufficient heat is applied. 3I at LS is obliterating these rules with the casual indifference of a cosmic anarchist. The physics of comet behavior seemed so well understood that scientists could predict with remarkable accuracy when and where comets would become active. The process follows what's known as the frost line or snow line concept, specific distances from the Sun where different materials transition from solid to gas. Water ice, the most common volatile material in comets, typically begins sublimating somewhere between 2.5 and 2.7 astronomical units from the Sun, depending on the specific conditions and composition of the object. This predictability has been confirmed by thousands of observations over centuries of comet study. Halley's Comet, Hale-Bopp, and countless other periodic visitors have followed these rules with clockwork precision, becoming active as they approach the inner solar system and falling dormant as they retreat to the outer reaches. The mathematical models describing this behavior are so reliable that they're used to predict comet appearances decades in advance and plan spacecraft missions to intercept them at optimal viewing distances. But 3I at LS is rewriting the textbook. At 2.9 astronomical units, it's operating in what should be the dead zone, a region where solar heating is insufficient to drive significant sublimation. The energy flux from the Sun at that distance is only about 12% of what Earth receives, barely enough to warm surface materials above the temperatures where water ice remains stable. Yet here it is, losing 40 kilograms of water per second in a continuous violent process that suggests internal temperatures and energy sources completely unaccounted for by standard models. The thermodynamics simply don't add up using conventional calculations. Sublimation requires approximately 2.8 million joules of energy per kilogram of water ice. At 40 kilograms per second, 3I at LS would need to be receiving and processing 112 million joules of energy every second just to drive the water loss we're observing. At its distance from the Sun, the available solar energy per square meter is only about 190 watts, insufficient by orders of magnitude to explain the observed activity. This energy deficit has forced scientists to consider mechanisms that exist far outside the standard comet behavior models. One possibility involves radioactive decay within the comet's interior. If 3I at LS contains significant amounts of radioactive isotopes, elements that were more abundant in the early galaxy when it formed, the continuous decay of these materials could provide internal heating sufficient to maintain liquid water or drive sublimation from within. The age factor makes this radioactive heating hypothesis particularly intriguing. If 3I at LS is indeed 3 billion years older than our solar system, it formed when the galaxy contained higher concentrations of short-lived radioactive isotopes produced by earlier generations of massive stars. Elements like aluminum-26, iron-60, and others with half-lives measured in millions of years could have been incorporated into the comet's structure during its formation, providing a long-term internal heat source that has kept it active throughout its interstellar journey. Another possibility involves the comet's internal structure and composition. Rather than being a solid monolithic object like many solar system comets, 3I at LS might be what planetary scientists call a contact binary, or rubble pile, multiple smaller objects that have gravitationally aggregated over time. The weak gravitational binding and loose structure of such objects can create internal friction as they rotate and flex during their journey through space, converting mechanical energy into heat through a process similar to tidal heating. This structural heating mechanism could explain why 3I at LS maintains such consistent activity levels. Unlike surface heating from solar radiation, which varies with rotation and orientation, internal friction heating would remain relatively constant as long as the object continues moving and rotating. The gravitational interactions with the Sun and planets as it passes through our solar system could even enhance this effect, creating additional tidal stresses that amplify the internal heating. But perhaps the most revolutionary possibility is that 3I at LS represents a completely different class of object than anything we've previously encountered. The chemical composition analysis from Swift Observatory suggests isotopic ratios and molecular signatures that don't match typical solar system materials. This could indicate formation conditions and chemical processes that simply don't exist in our local stellar environment. Consider the implications if 3I at ALS formed around a more massive star than our Sun. It might have experienced different thermal processing during its early history. Massive stars produce more intense radiation fields and have shorter lifetimes, potentially creating chemical compounds and crystalline structures that remain stable under conditions that would destroy typical solar system materials. These exotic compositions could exhibit sublimation behaviors and thermal properties that violate all our Earth-based assumptions about how ice and rock should behave in space. The violation of physical rules extends beyond just thermodynamics. 3I at LS is also challenging our understanding of comet orbital mechanics. Traditional comets show predictable changes in orbital velocity as they approach and recede from the Sun, following precise gravitational calculations. But interstellar objects like 3I at LS introduce new variables. They're not gravitationally bound to our solar system. Their trajectories are influenced by the galactic rotation and stellar encounters over millions of years, and their internal structure and composition may create unexpected rocket-like forces as material is ejected. The water outgassing from 3I at LS isn't just a passive release of material, it's creating thrust. Every molecule of water vapor ejected from the comet's surface carries momentum, and when millions of molecules per second are being expelled preferentially in certain directions, the cumulative effect can subtly alter the object's trajectory. This outgassing pressure has been observed in solar system comets, but the scale of water loss from 3I at LS could be creating orbital perturbations that don't fit standard gravitational models. The spectroscopic data reveals another rule-breaking aspect. The composition of the water itself, terrestrial water and water from solar system comets, show specific ratios of hydrogen isotopes, primarily regular hydrogen, with trace amounts of deuterium. The deuterium to hydrogen ratio serves as a fingerprint for the formation environment, reflecting the temperature and chemical conditions present when the water originally condensed from gas to ice. 3I at LS water shows isotopic signatures that suggest formation in a stellar environment with different chemical evolution than our own solar system. The deuterium ratios, oxygen isotope abundances, and trace chemical contaminants all point to nucleosynthesis processes and stellar metallicity that don't match solar values. It's as if the water itself is speaking in a foreign chemical dialect, revealing formation conditions that challenge our understanding of how stellar systems evolve and produce the raw materials for planet formation. This chemical foreignness has profound implications for astrobiology and the search for life beyond Earth. If the basic building blocks of life, water, organic compounds, and complex chemistry can form under such diverse conditions and remain stable during intergalactic journeys lasting billions of years, It suggests that life's ingredients are far more robust and widely distributed than previously imagined. The rule-breaking behavior of 3I at LS is forcing a fundamental reassessment of planetary science. Every assumption about comet behavior, thermal processing, chemical stability, and orbital mechanics is being tested against this single extraordinary object. And in many cases, our models are failing the test. But rather than viewing this as a crisis, scientists are embracing 3I at LS as a teacher, a cosmic professor delivering lessons about the true diversity and complexity of the universe. Each rule it breaks reveals new possibilities, new mechanisms, and new frontiers for exploration. The physics textbooks aren't wrong. They're just incomplete, and 3I at LS is showing us exactly what we still have to learn about the cosmos we inhabit. When Dennis Bodowitz spoke those profound words, "When we detect water from an interstellar comet, we're reading a note from another planetary system," he wasn't just describing a scientific observation, he was articulating a fundamental shift in how we understand life's place in the universe. The water streaming from 3I at LS isn't just H2O molecules, it's a chemical letter written in the language of stellar nucleosynthesis, carrying news from a world that formed around an alien sun billions of years before Earth existed. To understand the true significance of this interstellar water detection, you need to appreciate water's unique role in the chemistry of life. Water isn't just another chemical compound, it's the universal solvent that makes complex chemistry possible. Its molecular structure allows it to dissolve more substances than any other liquid, facilitating the chemical reactions that build proteins, enable cellular metabolism, and support the intricate molecular machinery that defines living systems. But water's biological importance extends far beyond its solvent properties. The hydrogen bonds between water molecules create unique thermal properties that stabilize temperature in biological systems. Water's high specific heat capacity means it can absorb large amounts of energy before its temperature changes significantly, providing thermal buffering that protects delicate biological molecules from temperature fluctuations. This thermal stability is crucial for maintaining the precise chemical conditions necessary for life. The detection of water from 3I at LS reveals that these life-enabling properties aren't unique to our solar system. The molecular structure of water, two hydrogen atoms bonded to one oxygen atom, represents one of the simplest possible configurations for creating hydrogen-bonded networks. Yet this simplicity belies its profound importance. Water's emergence requires the presence of both hydrogen and oxygen in the right proportions, along with temperature and pressure conditions that allow chemical bonding without destroying the resulting molecules. The fact that 3I at LS contains substantial amounts of water ice tells us that its origin stellar system achieved the chemical complexity necessary for water formation. This isn't trivial. It requires stellar nucleosynthesis processes that created sufficient oxygen, a relatively heavy element produced only in stellar cores, hydrogen, the most abundant element in the universe, and conditions cool enough for these elements to bond together, rather than remaining as separate plasma. The isotopic analysis of 3I at LS water reveals even deeper insights about its stellar birthplace. The ratio of deuterium to regular hydrogen in water molecules serves as a chemical fossil record of the temperature and density conditions present when the water originally formed. Deuterium, a heavy isotope of hydrogen containing a neutron as well as a proton, forms through specific nuclear processes and becomes incorporated into water molecules at rates that depend on the local stellar environment. The deuterium signature in 3I at LS water suggests formation conditions that were both similar to and subtly different from those in our own solar system. The basic chemical processes were the same: stellar fusion creating heavy elements, planetary disk formation, allowing chemical condensation, and thermal conditions enabling water-ice stability. But the specific ratios reveal a stellar environment with different metallicity, different temperatures during planetary formation, and possibly different stellar mass than our Sun. This chemical similarity with variation has profound implications for astrobiology. It suggests that water formation is a robust process that occurs across a wide range of stellar environments and galactic conditions. The universe appears to be remarkably efficient at creating the molecular foundations for life, producing water under diverse conditions and preserving it in stable forms that can survive intergalactic journeys lasting billions of years. But the significance extends beyond just water itself. Where water exists, other complex chemistry becomes possible. The spectroscopic analysis of 3I at LS has revealed not just water vapor, but also traces of other molecules that form the foundation of organic chemistry. Carbon dioxide, detected in earlier observations, provides the carbon-oxygen backbone for organic compound formation. Combined with water's hydrogen content, these elements create the basic building blocks for amino acids, proteins, and the complex carbon chemistry that characterizes life. The preservation of these chemical signatures over billions of years speaks to the remarkable stability of organic chemistry in the deep freeze of interstellar space. Unlike the constant thermal processing that occurs in the inner regions of stellar systems, the outer reaches where comets form and spend most of their existence provide nearly perfect preservation conditions. Temperatures just a few degrees above absolute zero prevent chemical decomposition, while the vacuum of space eliminates oxidation and other chemical degradation processes. 3I at LS has been a chemical time capsule, preserving pristine samples of the molecular inventory present in its birth stellar system billions of years ago. The water molecules streaming from its surface today contain the same isotopic ratios, the same chemical impurities, and the same molecular signatures that existed when its parent star was young and its planetary system was forming. It's as if we're receiving a chemical telegram from the deep past. Written in the universal language of atomic structure and molecular bonding, the universality of this chemistry is perhaps the most profound revelation. Despite forming in a completely different stellar environment, around a different star, billions of years ago, 3I at LS contains the same basic life-enabling molecules that characterize our own solar system. Their isotopic ratios are different, reflecting different formation conditions, but the fundamental chemistry is recognizably similar. Water is still water, carbon dioxide is still carbon dioxide, and the potential for complex organic chemistry remains intact. This chemical universality suggests that the ingredients for life are not rare, exotic, or dependent on highly specific conditions. Instead, they appear to be natural products of stellar and planetary evolution, emerging wherever the right combination of elements, temperatures, and timescales come together. The universe seems to be not just capable of producing life's building blocks, but actively inclined toward their formation and preservation. The detection of complex organic molecules in 3I at LS also challenges our understanding of how life's chemistry can survive in the harsh environment of interstellar space. For billions of years, this comet has been exposed to cosmic radiation, ultraviolet light from distant stars, and the extreme cold of the interstellar medium. Yet the chemical signatures remain intact, suggesting either remarkable molecular stability or ongoing chemical processes that continuously regenerate life's building blocks, even in the apparent sterility of deep space. Recent theoretical work suggests that interstellar objects like 3I at LS might actually be sites of ongoing chemistry rather than just passive preservers of ancient materials. The internal heating that drives water outgassing could also facilitate slow chemical reactions between different molecular species within the comet's interior. These reactions might produce complex organic compounds over geological timescales, essentially using the comet as a slow-motion chemical laboratory during its journey between the stars. If this hypothesis proves correct, it would mean that 3I at LS isn't just carrying the chemical legacy of its birth system. It's actively evolving that chemistry during its interstellar journey. The water and organic compounds we're detecting might include both ancient materials preserved from its origin and new compounds created through billions of years of slow chemical processing in the comet's interior. The implications for the distribution of life in the universe are staggering. If interstellar objects like 3I at LS are not just carrying life's ingredients but actually enriching and evolving them during their cosmic journeys, then every stellar system is connected through a network of chemical exchange that spans the galaxy. Complex organic molecules developed in one stellar system could seed planet formation in distant systems, creating a galactic web of chemical evolution that makes life more probable, more diverse, and more widespread than any Earth-centric model could predict. 3I at LS is teaching us that we live in a chemically connected universe, where the molecular foundations of life are continuously exchanged between stellar systems through the wanderings of interstellar visitors. The note from another planetary system that Dennis Bodowitz described isn't just a historical record, it's part of an ongoing conversation between worlds, written in the universal language of chemistry, and delivered by cosmic messengers that have been traveling the galaxy since before our world existed. Every molecule of water streaming from 3I at LS carries this message: the chemistry of life is not a rare accident. but a natural consequence of cosmic evolution. And in a universe where such chemistry can survive billion-year journeys between the stars, life itself becomes not just possible but probable. As scientists grappled with the impossible reality of 3I at LS, spraying water at distances where it should be frozen solid, a remarkable theory began to emerge from the data. Rather than traditional surface sublimation, the comet might be operating like a cosmic steam engine, powered by a distributed network of miniature steam vents hidden within its structure. This hypothesis not only explains the anomalous water activity, but reveals a completely new mechanism for how interstellar objects can remain active during their billion-year journeys through space. The breakthrough came when scientists combined observations from multiple instruments, creating a three-dimensional picture of how water was being distributed around 3I at LS. The Swift Observatory's ultraviolet detections showed hydroxyl radicals throughout the comet's coma, but near-infrared observations from the Gemini South Telescope and NASA's Infrared Telescope facility revealed something unexpected: discrete chunks of ice floating in the cloud of gas and dust surrounding the nucleus. These ice chunks weren't part of the comet's solid nucleus. They were separate objects, ranging in size from pebbles to boulders, drifting in the gravitational field around 3I at LS, like a miniature asteroid belt. But unlike typical debris ejected from comet surfaces, these icy fragments showed signs of active sublimation, each one acting like a tiny steam vent releasing water vapor as sunlight warmed their surfaces. The physics of this distributed sublimation system are elegant and surprising. While the main nucleus of 3I at LS remains too cold for significant surface activity at 2.9 astronomical units, the smaller ice chunks have much higher surface area to volume ratios, making them far more susceptible to solar heating. A fragment the size of a basketball has orders of magnitude more surface area per unit mass than the multi-mile wide nucleus, allowing solar radiation to penetrate and warm the entire chunk rather than just heating a thin surface layer. This size-dependent heating effect explains why 3I at LS can maintain such high water activity at distances where larger objects remain dormant. The comet isn't violating the laws of physics. It's exploiting them through a mechanism that nature never had the opportunity to perfect in our solar system. The combination of interstellar composition, ancient internal structure, and precise size distribution of ejected fragments creates conditions that simply don't exist among objects native to our stellar neighborhood. But how did these ice chunks become separated from the main nucleus in the first place? The answer lies in 3I at LS's extraordinary journey through interstellar space. Unlike solar system comets, which spend most of their time in stable, predictable orbits, 3I at LS has been subjected to billions of years of gravitational perturbations, stellar encounters, and cosmic bombardment that gradually loosened its internal structure. The process likely began early in the comet's history, when gravitational interactions with its parent star and planetary system ejected it into interstellar space. The transition from bound to unbound orbit would have subjected 3I at LS to enormous tidal stresses, potentially fracturing its interior and creating networks of cracks and voids that weakened its structural integrity. Over geological timescales, these fractures would have propagated through the nucleus, creating a complex internal architecture of loosely bound fragments. During its interstellar journey, additional stresses from galactic rotation, encounters with molecular clouds, and gravitational interactions with passing stars would have continued this fragmentation process. Rather than remaining a solid, monolithic object, 3I at LS evolved into what planetary scientists term a rubble pile, a gravitationally bound collection of smaller fragments with significant void spaces between them. The internal structure revealed by this fragmentation process helps explain another puzzling aspect of 3I at LS's behavior: the consistency of its water output. Traditional surface sublimation varies dramatically as different regions of a comet's nucleus are exposed to sunlight during rotation. But if water release is dominated by hundreds or thousands of small fragments distributed throughout the coma, each at different distances from the nucleus and in different phases of sublimation, the combined output would naturally tend towards statistical averaging. The steam vent theory also explains why 3I at LS shows such a high percentage of active surface area compared to typical solar system comets. The 8% activity level that initially puzzled scientists makes perfect sense if you consider that the active surface includes not just the main nucleus but hundreds of smaller fragments, each contributing to the total water output. according to its size, distance from the sun, and exposure to solar radiation. Spectroscopic analysis supports this distributed source model. The hydroxyl radicals detected by SWIFT show velocity distributions consistent with release from multiple sources at different distances from the central nucleus. Rather than the focused directional jets typical of surface venting, the OH signature suggests a diffuse multi-source origin that matches the miniature steam vent hypothesis perfectly. The thermal modeling of these ice fragments reveals fascinating details about their sublimation behavior. Unlike the main nucleus, which can only heat its surface layer while maintaining a cold interior, fragments smaller than a few meters across can be heated throughout their entire volume by solar radiation. This uniform heating allows them to maintain sublimation temperatures even at distances where larger objects remain frozen, effectively extending the active zone far beyond the traditional frost line. The size distribution of these fragments appears to follow what mathematicians call a power law. There are many small fragments, fewer medium-sized ones, and very few large chunks. This distribution maximizes the total surface area available for sublimation, while ensuring that most fragments remain small enough for efficient heating. It's as if billions of years of cosmic weathering have naturally optimized 3I at LS for maximum water release efficiency. But the steam vent mechanism involves more than just passive solar heating. As ice fragments sublimate and lose mass, they become even more susceptible to heating, creating a positive feedback loop that accelerates the sublimation process. Smaller fragments heat faster, sublimate more efficiently, and break apart into even smaller pieces that heat even faster. This cascading fragmentation process could explain why 3I at LS maintains such consistent activity levels. The system naturally regulates itself to maintain optimal fragment sizes for continued sublimation. The longevity of this process is remarkable. Computer simulations suggest that a rubble pile structure like 3I at LS could continue releasing fragments and maintaining active sublimation for millions of years, gradually dispersing its mass throughout the solar system as a network of active ice chunks. This extended activity timeline means that interstellar visitors might remain observable and scientifically valuable long after traditional comets would have become dormant. The miniature steam vents theory has implications that extend far beyond explaining 3I at LS's unusual behavior. If this mechanism is common among interstellar objects, it suggests that the space between stars is filled with active, evolving chemistry rather than just cold, inert debris. Each interstellar comet becomes a mobile chemical laboratory, continuously processing and releasing molecular materials as it travels between stellar systems. This distributed chemical processing could play a crucial role in seeding new stellar systems with the organic compounds necessary for planet formation and potential life development. Rather than requiring each stellar system to independently develop complex chemistry, interstellar visitors like 3I at LS could serve as chemical couriers, delivering pre-formed organic molecules and water to emerging planetary systems throughout the galaxy. The steam vent mechanism also provides a new framework for understanding how life's building blocks could remain active and available, even in the apparent sterility of interstellar space. Rather than simply preserving ancient chemistry in frozen form, objects like 3I at LS are actively processing and releasing these materials in ways that could influence the chemical evolution of entire galactic regions. As 3I at LS continues its journey through our solar system, its network of miniature steam vents continues operating, each tiny fragment contributing to the cosmic symphony of chemical release that makes this interstellar visitor one of the most active and informative objects ever observed. The theory that emerged to explain its impossible behavior has opened entirely new chapters in our understanding of interstellar chemistry, planetary formation, and the mechanisms by which life's ingredients travel between the stars. The numbers were so startling that scientists initially questioned their own calculations. Traditional comets from our solar system typically show between 3% and 5% of their surface area actively venting material, even when they're much closer to the sun and receiving significantly more solar heating. 3I at LS, operating at 2.9 astronomical units where it should be completely dormant, was showing activity levels suggesting that at least 8% of its surface was actively releasing material into space. This wasn't just an anomaly. It was a fundamental challenge to everything scientists thought they understood about how comets work. To appreciate the magnitude of this discovery, you need to understand what active surface area means in comet science. Comets aren't uniformly active across their entire surface. Instead, they develop discrete active regions, areas where the protective layer of dust and debris has been stripped away, or where internal heating has created pathways for subsurface ice to sublimate directly into space. These active regions function like natural steam vents, channeling the outgassing that creates a comet's characteristic tail and coma. The percentage of active surface area has been one of the most reliable predictors of comet behavior for decades. This measurement allows scientists to estimate total mass loss rates, predict how long a comet will remain active, and understand the internal structure and composition of the nucleus. The consistency of this 3 to 5% range across hundreds of observed comets suggested a fundamental physical constraint on how much of a comet's surface can simultaneously contribute to outgassing. That constraint made perfect sense from a thermal physics perspective. Solar heating can only penetrate a limited distance into the comet's surface before being absorbed or conducted away by the surrounding material. This creates a thermal skin depth, typically just a few centimeters, beyond which temperatures remain too cold for sublimation to occur. The 3 to 5% active surface represents the maximum area where this thermal penetration can overcome the insulating effects of dust coverage and internal heat conduction. 3I at LS is obliterating these thermal constraints with its 8% activity level, suggesting either a completely different internal structure or heating mechanisms that don't depend on surface solar absorption. The implications cascade through every aspect of comet science. If interstellar objects can maintain such high activity levels at extreme distances, then our models for comet evolution, mass loss, and orbital dynamics need fundamental revision. The surface activity calculation itself required extraordinary precision in measurement and analysis. Scientists had to combine observations from multiple instruments to build a complete picture of 3I at LS's mass loss and surface characteristics. The Swift Observatory provided data on hydroxyl radical production rates, which directly correlate with water sublimation. Infrared observations revealed the total thermal emission from the nucleus, allowing estimates of surface temperature and heating distribution. Visible light measurements showed the size and density of the coma, providing constraints on total material production rates. Integrating these diverse data sources required sophisticated modeling that accounted for the complex physics of sublimation, gas dynamics, and radiation transport. The team had to consider how water molecules transition from solid to gas, how the resulting vapor expands into the surrounding space, how solar radiation breaks apart those molecules into hydroxyl radicals, and how those radicals emit the ultraviolet light that Swift detected. Each step involved quantum mechanical processes, thermodynamic calculations, and fluid dynamic modeling that pushed the limits of computational comet science. The 8% result emerged from this analysis with uncomfortable consistency across multiple independent measurement techniques. No matter how the scientists approached the calculation, whether starting from hydroxyl detection rates, thermal emission models, or coma density measurements, they arrived at the same conclusion: 3I at LS was far more active than any comet had a right to be at such distances from the Sun. But the surface activity surprise revealed more than just anomalous numbers. The spatial distribution of active regions on 3I at LS appeared to be fundamentally different from typical solar system comets. Rather than showing the concentrated jets and discrete venting areas characteristic of nucleus-based outgassing, the activity seemed more distributed and diffuse. This suggested that the traditional model of comet activity, localized surface heating driving sublimation from specific active regions, might not apply to interstellar visitors. The distributed activity pattern supports the miniature steam vents hypothesis discussed earlier, but it also raises intriguing questions about the internal structure of 3I at LS. If 8% of its surface is active, either the object has an unusually porous structure that allows internal heating to reach much larger surface areas, or the heating mechanisms themselves are distributed throughout the nucleus rather than concentrated at the surface. One possibility involves what planetary scientists call Swiss cheese structure, a nucleus riddled with internal voids and channels that allow subsurface ice to sublimate and vent through a network of surface openings. This structure could develop naturally in objects that have experienced billions of years of thermal cycling, internal chemical reactions, and gravitational stresses during interstellar travel. The resulting architecture would have much higher effective surface area for sublimation than the simple geometric surface area would suggest. Another explanation involves the age and composition differences between 3I at LS and solar system comets. Objects that formed 7-8 billion years ago in different stellar environments might contain radioactive isotopes, exotic ices, or crystalline structures that don't exist in younger, local comets. These ancient materials could exhibit sublimation behaviors and thermal properties that enable much higher activity levels under conditions where typical comets remain dormant. The isotopic analysis of water from 3I@LS provides some support for this compositional explanation. The deuterium to hydrogen ratios and oxygen isotope signatures suggest formation in a stellar environment with different chemical evolution than our solar system. These chemical differences could reflect not just different raw materials but different physical processes during the comet's formation that created internal structures more conducive to distributed outgassing. The high activity level also has profound implications for 3I@LS's longevity and evolution. If it continues losing 40 kilograms of water per second, a rate supported by the 8% surface activity, the comet will lose substantial mass during its passage through our solar system. Computer models suggest that objects maintaining such high mass loss rates cannot survive for the billions of years that 3I@LS appears to have existed, unless they started with much larger initial masses or possess internal mass reservoirs that aren't apparent from external observations. This longevity paradox suggests that 3I@LS might be experiencing a period of enhanced activity triggered by its encounter with our solar system. The gravitational perturbations from the Sun and planets, combined with the increased solar heating as it approaches perihelion, could be activating previously dormant internal regions or destabilizing the object's structure in ways that dramatically increase sublimation rates. If this enhanced activity is temporary, it means we're witnessing 3I@LS during a brief period of maximum scientific interest. The high activity levels that make it such a valuable target for chemical analysis might also represent the beginning of its structural disintegration, as the elevated mass loss rates gradually disperse the material that has held it together during its interstellar journey. The surface activity surprise has also prompted a reassessment of how scientists search for and classify interstellar objects. If visitors from other stellar systems can maintain such high activity levels at large solar distances, then survey programs need to expand their search parameters to include objects that would previously have been dismissed as too active to be interstellar in origin. The discovery suggests that the boundary between active and inactive objects is far more complex than previously imagined. Rather than simple on-off switches controlled by solar distance, comets might exist in a continuum of activity states that depend on internal structure, composition, thermal history, and dynamic evolution during their cosmic journeys. 3I@LS is teaching us that surface activity isn't just about proximity to the Sun, it's about the complex interplay between stellar environment, formation chemistry, internal structure, and evolutionary history that creates objects far more diverse and surprising than our solar system-based models ever predicted. The 8% activity level that initially seemed impossible is now opening new frontiers in understanding how water, life's most essential molecule, behaves in the cosmic environments where it spends most of its existence. The surface activity surprise continues to challenge scientists as 3I@LS proceeds through our solar system, maintaining activity levels that shouldn't exist while simultaneously providing the most detailed chemical analysis of interstellar material ever achieved. Each measurement confirms that we're witnessing something unprecedented, a visitor from deep space that refuses to follow the rules we've spent centuries establishing. To understand just how extraordinary 3I@LS truly is, you must first journey back through the brief but revelatory history of interstellar visitors to our solar system. Each of these cosmic wanderers has arrived like a messenger from distant worlds, carrying secrets that challenge our understanding of how planets form, how chemistry evolves, and what possibilities exist in the vast spaces between stars. But the pattern that emerges from their diverse behaviors tells a story even more surprising than any individual discovery. The first chapter of this interstellar saga began on October 19, 2017, when astronomer Robert Weryk spotted something unusual in data from the Pan-STARRS 1 telescope in Hawaii. Initially catalogued as a typical asteroid, the object designated 1I/Oumuamua, Hawaiian for messenger from afar, arriving first, quickly revealed itself to be anything but typical. Its trajectory calculations showed something impossible. It was moving too fast to be gravitationally bound to our solar system. This was our first confirmed interstellar visitor. Oumuamua's behavior confounded every expectation scientists had developed about interstellar objects. Rather than the icy comet-like composition predicted by theoretical models, it appeared completely dry, showing no signs of water vapor, no visible tail, no coma of gas and dust. Its elongated shape, estimated at roughly 400 meters long and only 40 meters wide, resembled nothing so much as a cosmic cigar tumbling end over end, as it raced through our solar system at 26 kilometers per second. But Oumuamua most puzzling characteristic was its inexplicable acceleration. As it rounded the sun and began its journey back toward interstellar space, precise tracking revealed that it was moving slightly faster than gravitational calculations predicted. Something was providing additional thrust, yet no outgassing or material ejection could be detected. The mystery deepened when scientists realized that this acceleration was decreasing over time, following a pattern that suggested some form of outgassing that remained invisible to all instruments. The scientific community was divided. Some proposed that Oumuamua might be composed of exotic materials like metallic hydrogen that could sublimate without producing detectable signatures. Others suggested it might be artificially constructed, a hypothesis that gained serious consideration in peer-reviewed publications before being ultimately rejected due to lack of supporting evidence. The most widely accepted explanation involved outgassing of materials too sparse or exotic to detect with available instruments, but this required assuming compositions and behaviors unlike anything previously observed. Oumuamua's brief visit, lasting only a few months within optimal observation range, left more questions than answers. Its completely dry nature challenged predictions that interstellar space should be filled with icy objects similar to solar system comets. Its unusual shape and rotation suggested formation processes or evolutionary histories unlike anything in our local stellar neighborhood. Most puzzling of all, its invisible propulsion mechanism implied physical processes that existed at the very edge of detectability, hinting at the diversity of materials and behaviors that might characterize objects from different stellar environments. The second chapter began on August 30th, 2019, when Gennady Borisov, an amateur astronomer in Crimea, discovered what would become known as 2I/Borisov. Unlike its enigmatic predecessor, Borisov behaved much more like scientists expected an interstellar comet to behave. It developed a visible coma and tail, showed clear signs of outgassing, and maintained activity levels that correlated reasonably well with its distance from the Sun. But Borisov's apparent normalcy concealed its own set of surprises. Spectroscopic analysis revealed that its coma was unusually rich in carbon monoxide, concentrations higher than typically observed in solar system comets. This chemical signature suggested formation in a much colder environment than characterizes our own stellar system's outer regions. The high CO content implied that Borisov originated in a stellar environment where temperatures remained low enough for carbon monoxide to condense and remain stable for billions of years. The carbon monoxide abundance in Borisov provided crucial insights into the diversity of stellar system chemistry. In our solar system, Colorado is typically destroyed or driven off during the early thermal processing that occurs as planets form and the young sun increases in luminosity. But Borisov's composition suggested formation around a smaller, cooler star or in outer regions of a stellar system that never experienced significant thermal processing. Detailed observations of Borisov also revealed an unusual nuclear structure. Rather than the relatively dense, cohesive nuclei characteristic of solar system comets, Borisov appeared to have lower density and possibly more fragile internal structure. This difference might reflect formation mechanisms that don't occur in our stellar system, or evolutionary processes during its interstellar journey that gradually altered its physical properties. Perhaps most intriguingly, Borisov showed evidence of internal chemistry that remained active even during its long journey through interstellar space. The specific ratios of different molecular species in its coma suggested ongoing chemical reactions within the nucleus, possibly driven by radioactive decay or cosmic ray bombardment. This implied that interstellar objects weren't just passive preservers of ancient chemistry, but active processes that continue evolving their compositions during their cosmic wanderings. The pattern that emerged from these first two interstellar visitors was clear. Each object was unique, carrying chemical and physical signatures that reflected the diverse conditions present in different stellar systems. Rather than finding objects that matched solar system templates, scientists discovered that interstellar visitors represented an entirely different category of cosmic chemistry and evolution. This diversity principle makes 3I at Lao's water outgassing all the more significant. where Oumuamua was dry and mysterious, and Borisov was rich in exotic ices, 3I at Laos is abundantly wet and impossibly active. The progression suggests that stellar systems throughout the galaxy produce fundamentally different types of objects, each reflecting unique formation conditions, chemical evolution, and physical processes. The chemical diversity observed across these three visitors provides compelling evidence for what astronomers call the stellar metallicity hypothesis, the idea that stars with different masses, ages, and chemical compositions produce planetary systems with distinctly different characteristics. Low metallicity stars might produce objects like Oumuamua, with unusual compositions and exotic behaviors. High metallicity systems might create objects like Borisov, with complex chemistry and unusual molecular abundances. And systems with different thermal histories might produce objects like 3I at LS, with internal heating mechanisms and structural properties that enable sustained activity far from any star, but the diversity extends beyond just chemical composition. Each interstellar visitor has shown different responses to the solar environment, different internal structures, and different evolutionary trajectories. This variability suggests that interstellar space contains a vast library of different object types, each representing different chapters in the galactic story of planetary formation and chemical evolution. The timing of these discoveries is also revealing. 3 confirmed interstellar visitors in less than a decade suggests that such objects are far more common than previously imagined. Improved detection capabilities and expanded sky surveys are revealing that our solar system is constantly being visited by objects from other stellar systems. We're not living in cosmic isolation. We're part of a dynamic, interconnected galaxy where material regularly flows between stellar systems. Each visitor provides a unique window into conditions that exist nowhere in our local stellar environment. Oumuamua offers insights into exotic compositions and formation mechanisms. Borisov reveals the chemistry of extremely cold stellar environments. 3I at LS demonstrates active chemistry and internal heating that persist across interstellar distances and billion-year timescales. Together, these 3 visitors are rewriting our understanding of how stellar systems work, how planets form, and how chemistry evolves in the galaxy. They're teaching us that the universe is far more diverse, far more active, and far more interconnected than any Earth-based models ever predicted. The secrets carried by these previous visitors have prepared the scientific community to better understand 3I at LS's impossible behavior, rather than dismissing its water outgassing as instrument error or calculation mistake. Scientists now recognize it as the latest chapter in an ongoing revelation about galactic diversity. Each interstellar visitor builds on the lessons learned from its predecessors, gradually revealing the true complexity and wonder of the cosmic environment we inhabit. As 3I at LS continues its journey through our solar system, it carries forward this tradition of surprise and discovery. But its active chemistry and sustained outgassing represent a new category of interstellar visitor, one that's actively communicating its chemical secrets rather than hiding them in exotic compositions or invisible behaviors. In the symphony of interstellar chemistry, 3I at LS is playing the loudest, clearest note yet heard from the space between stars. In early October 2025, as 3I at LS continued its relentless journey through our solar system, spraying its ancient water into the cosmic void, something remarkable happened. The European Space Agency's Mars orbiters, designed to study the red planet's atmosphere and surface, suddenly became witnesses to an extraordinary cosmic encounter. 3I at LS passed within 30 million kilometers of Mars, close enough for the planet's sophisticated orbital instruments to capture unprecedented detailed observations of an active interstellar visitor. The timing of this encounter was fortuitous beyond scientific planning. Mars, positioned at the right place in its orbit at the right moment in history, became humanity's best observation platform for studying 3I at LS during a crucial phase of its solar system transit. The red planet's collection of orbiting spacecraft, including the Mars Express, the ExoMars Trace Gas Orbiter, and several other active missions, suddenly transformed from planetary science instruments into interstellar object analyzers. The 30 million kilometer distance might seem vast in terrestrial terms, but in astronomical context it represented an incredibly close encounter. To put this in perspective, when Mars and Earth are at their closest approach, they're separated by approximately 55 million kilometers at best. 3I at LS passed nearly twice as close to Mars as Mars ever gets to Earth, providing observation opportunities that surpassed anything possible from our home planet. The Mars orbiter's instruments weren't designed for comet observation, but their capabilities proved remarkably well suited to studying 3I at LS. The Trace Gas Orbiter's spectrometers, originally intended to analyze the Martian atmosphere for traces of methane and other gases, could detect the molecular signatures in 3I at LS's expanding coma. Mars Express's high-resolution cameras, designed to map Martian terrain, captured detailed images of the comet's nucleus and surrounding material distribution. But perhaps most valuable were the plasma and magnetic field instruments aboard the Mars orbiters. These sensors, designed to study Mars's interaction with the solar wind, suddenly found themselves measuring how 3I at LS's outgassing creates its own local space environment. The water vapor streaming from the comet at 40 kilograms per second doesn't just disappear into space. It creates a complex plasma environment as solar radiation ionizes the molecules and the solar wind interacts with the resulting charged particles. The data revealed that 3I at LS is surrounded by what scientists term a plasma sheath, a region of ionized gas that extends far beyond the visible coma. This plasma environment has its own magnetic field characteristics, density gradients, and dynamic behavior that creates a miniature version of the complex plasma physics that occurs around planets and moons. 3I at LS isn't just releasing water, it's creating its own localized space weather system. The Mars encounter also provided crucial information about 3I at LS's internal structure and composition. As the comet passed through Mars's gravitational field, sensitive accelerometers aboard the orbiters detected minute changes in the spacecraft trajectories that revealed the comet's mass distribution. These gravitational measurements, combined with optical observations of its size and shape, allowed scientists to calculate density estimates that constrain models of the comet's internal structure. The density calculations revealed another surprise. 3I at LS appears to have significantly lower density than typical solar system comets. This low density supports the rubble pile hypothesis, the idea that the comet consists of loosely aggregated fragments rather than a solid cohesive nucleus. The gravitational data suggests that as much as 40% of 3I at LS's volume might consist of empty space between loosely bound chunks of ice and rock. This porous structure explains several puzzling aspects of the comet's behavior. The high surface activity percentage makes sense if the surface includes internal cavities and channels where sublimation can occur throughout the object's interior. The sustained water outgassing becomes possible if solar heating can penetrate through the porous structure, warming ice deposits far below the geometric surface. The consistent activity levels result from the distributed nature of sublimation sites throughout the loosely bound structure. The Mars orbiters also captured something unprecedented: real-time observations of 3I at LS's outgassing behavior. Unlike Earth-based telescopes, which see the comet as a point source or small disk, the Mars instruments could resolve spatial structure within the coma and track how different regions of the nucleus contribute to the overall water production. These observations revealed that the outgassing isn't uniform. Instead, it shows complex patterns that change over the comet's rotation period. The rotational analysis proved particularly revealing. 3I at LS rotates with a period of approximately 7.6 hours, and the Mars observations showed that water production varies significantly as different regions of the nucleus face the Sun. But unlike typical comets, which show dramatic on-off cycles as discrete active regions rotate in and out of sunlight, 3I at LS displays more gradual variations that suggest a more distributed source of activity. The encounter timing also allowed scientists to observe 3I at LS from multiple angles simultaneously. Earth-based telescopes could observe the comet from one direction while Mars orbiters viewed it from a completely different perspective, providing stereo observations that revealed three-dimensional structure in the coma and tail. This multi-viewpoint analysis showed that the water outgassing creates a complex asymmetric distribution of material that reflects both the comet's internal structure and its interaction with solar radiation and magnetic fields. Perhaps most importantly, the Mars encounter occurred during a period when 3I at LS was approaching its closest point to the Sun. The increased solar heating was beginning to drive even higher levels of activity, and the Mars instruments captured this transition in real time. The observations showed water production rates increasing steadily as the comet moved closer to perihelion, but the rate of increase was slower than predicted by standard comet models, again suggesting unusual internal structure or composition. The plasma measurements from Mars provided insights into how interstellar objects interact with the solar environment. As 3I@L's water vapor became ionized by solar radiation, it created a bow shock, a boundary where the solar wind encounters the comet's plasma environment and is deflected around it. This bow shock has characteristics different from those observed around solar system comets, reflecting the unusual composition and outgassing patterns of interstellar visitors. The Mars encounter also revealed temporal variations in 3I@L's activity that hadn't been detectable from Earth. The high-cadence observations possible from Mars orbit showed that water production rates fluctuate on timescales of hours to days, possibly reflecting changes in solar radiation, internal heating, or structural evolution as the comet responds to increasing solar heating. Data from the encounter continues to be analyzed, but initial results confirm that 3I@Ls represents a fundamentally new category of active solar system object. The combination of interstellar origin, unusual composition, anomalous structure, and extreme activity levels creates behaviors that don't match any existing theoretical models. The Mars observations provide the detailed measurements necessary to develop new models that can account for the diversity of interstellar visitors. The success of the Mars encounter has implications for future interstellar object studies. It demonstrates that planetary missions can serve double duty as interstellar visitor observatories when circumstances align properly. The serendipitous nature of this encounter, Mars happening to be in the right position when 3I@Ls passed through the inner solar system, highlights the importance of maintaining multiple observation platforms throughout the solar system. As 3I@Ls continued past Mars toward its closest approach to the Sun, the data collected during the encounter provided crucial context for interpreting subsequent observations. The Mars measurements established baselines for the comet's behavior, composition, and structure that allow scientists to distinguish between intrinsic properties of the object and changes induced by increasing solar heating. The Mars encounter represents a watershed moment in interstellar object research, the first time humanity has obtained detailed, multi-instrument observations of an active interstellar visitor from a platform other than Earth. The data collected during those few days in October 2025 will inform interstellar object research for decades to come, providing benchmarks for understanding how visitors from other stellar systems behave when they encounter the unique environment of our inner solar system. Beyond Mars, in the outer reaches of our solar system, the European Space Agency's Jupiter Icy Moons Explorer sits in a unique position that will soon make it the most important observer of 3I@Ls during the most crucial phase of the comet's journey. JUICE, currently positioned on the far side of the Sun from Earth, will have an unparalleled view of 3I@Ls immediately after its closest solar approach, when the interstellar visitor is expected to reach peak activity levels and reveal its deepest chemical secrets. The timing of JUICE's observation opportunity is both fortuitous and scientifically perfect. While Earth-based telescopes and Mars orbiters observed 3I@Ls as it approached the Sun, JUICE will witness the aftermath, the period when maximum solar heating has driven the comet's internal processes to their highest intensity. This post-perihelion phase often reveals chemical signatures and structural changes that remain hidden during the approach, as the accumulated thermal energy triggers delayed responses throughout the comet's interior. JUICE's instruments were designed to study the icy moons of Jupiter, Europa, Ganymede, and Callisto, which makes them ideally suited for analyzing water-rich objects like 3I@Ls. The spacecraft carries a sophisticated suite of spectrometers, cameras, and plasma instruments that can detect water in all its forms: ice, vapor, and ionized plasma. These capabilities will provide the most comprehensive chemical analysis of an interstellar object ever attempted. The spacecraft's MAGIS Moons and Jupiter Imaging Spectrometer instrument will be particularly valuable for studying 3I@Ls. MAGIS can simultaneously observe invisible, near-infrared, and short-wave infrared wavelengths, allowing it to detect water ice signatures, organic compounds, and trace gases that might be too faint for other instruments to observe. The spectrometer's high sensitivity and broad wavelength coverage make it capable of detecting molecular species that have never been observed in interstellar objects. But JUICE's most significant advantage isn't just instrumental, it's positional. While Earth-based observations are limited by atmospheric interference and day-night cycles, and while Mars orbiters observed 3I@Ls during a relatively brief encounter, JUICE can track the comet continuously for weeks or months as it retreats from the Sun. This extended observation period will reveal how 3I at Lesser's activity evolves over time, providing insights into the internal heating mechanisms and structural changes that drive its impossible water outgassing. The post-perihelion timing is crucial for understanding 3I at Lesser's internal structure. As the comet reaches its closest approach to the Sun, thermal waves will propagate inward from its surface, potentially reaching internal ice deposits that have remained frozen throughout its billions-year interstellar journey. The heat absorbed during perihelion passage doesn't immediately sublimate all available ice. Instead, it creates a thermal pulse that can drive activity for months or years after the closest solar approach. JUICE's observations will capture this delayed thermal response in unprecedented detail. The spacecraft's thermal infrared instruments can map temperature distributions across 3I, LS's surface and coma, revealing how heat propagates through the comet's structure and identifies regions of delayed outgassing. This thermal mapping will provide direct observational constraints on the internal structure models developed from Mars encounter data. The mission's 3GM Gravity and Geophysics of Jupiter and Galilean Moons instrument will attempt something never before achieved with an interstellar object: precision mass measurements using radio science techniques. By tracking minute changes in JUICE's radio signals as 3I at LS passes through the spacecraft's field of view, scientists can measure the comet's gravitational field with extraordinary precision. These measurements will reveal mass distribution, internal density variations, and structural asymmetries that remain invisible to optical observations. JUICE's plasma instruments will also provide unique insights into how 3I at LS interacts with the solar wind environment at different distances from the Sun. As the comet retreats from perihelion, its plasma environment will evolve, and JUICE can track these changes to understand how interstellar objects create and maintain their local space weather systems. This plasma analysis will complement the Mars observations to create a complete picture of 3I at Lesser's electromagnetic environment. The communication challenges facing JUICE add both complexity and anticipation to the observation campaign. Currently positioned on the far side of the Sun from Earth, the spacecraft must relay data through a slower backup antenna system that significantly reduces the data transmission rate. The high-resolution spectra, detailed images, and precise measurements that JUICE will collect of 3I at LS must be stored on board and transmitted slowly over the months following the observations. This communication delay means that the most detailed observations of 3I at LS during its peak activity phase won't reach Earth until February 2026. For the scientific community, this creates an unprecedented situation, knowing that crucial data exists but being unable to access it immediately. The delayed gratification adds an element of suspense to the 3I at LS story that reflects the inherent challenges of deep space exploration. ESA mission planners are optimizing JUICE's observation strategy to maximize scientific return despite the communication constraints. The spacecraft will prioritize the most scientifically valuable measurements for immediate transmission, while storing higher resolution data for later relay. This requires careful balance between getting quick results and preserving the most detailed information for comprehensive analysis. The scientific expectations for JUICE's observations are extraordinarily high. Unlike previous interstellar object encounters, which provided snapshots of visitor behavior, JUICE's will deliver a comprehensive portrait of how an interstellar comet responds to thermal processing in an alien stellar environment. The data will answer fundamental questions about internal structure, composition evolution, and the mechanisms that allow objects like 3I at LS to maintain chemical activity across interstellar distances. JUICE's spectroscopic capabilities will search for molecular species that have never been detected in interstellar objects. Complex organic compounds, rare isotope ratios, and exotic ice phases could reveal details about the chemistry of distant stellar systems and the processes that occur during billion-year journeys through interstellar space. Each new molecular detection will add another line to the chemical message that 3I at LS carries from its distant origin. The mission will also attempt to detect temporal variations in 3I at Lesser's composition as it retreats from the Sun. If the comet's internal structure includes multiple layers or regions with different chemical compositions, the changing thermal conditions might expose different materials over time. JUICE's extended observation period will capture these compositional variations and map them to specific regions or depths within the comet's structure. Perhaps most intriguingly, JUICE might observe 3I at LS during a period of structural evolution or fragmentation. The intense heating during perihelion passage could destabilize the comet's loosely bound internal structure, potentially causing it to break apart or significantly alter its outgassing patterns. If such dramatic changes occur, JUICE will be perfectly positioned to document the process in real time, providing unprecedented insights into how interstellar objects respond to stellar environments different from their origin systems. The data that JUICE collects will also establish important precedents for future interstellar object encounters. The observation techniques, analysis methods, and scientific insights developed for studying 3I at LS will inform strategies for investigating future interstellar visitors. Each encounter builds on previous experience, and JUICE's comprehensive study of 3I at LS will significantly advance our capabilities for extracting maximum scientific value from these rare cosmic opportunities. As 3I at LS approaches its closest point to the Sun and prepares for its encounter with JUICE's instruments, the scientific community waits with anticipation for what may be the most revealing observations of an interstellar object ever attempted. The data locked within JUICE's memory banks, slowly making its way toward Earth through the cosmic communication network, holds answers to questions about galactic chemistry, planetary formation, and the mechanisms that distribute life's building blocks throughout the universe. The JUICE mission's future observations of 3I at LS represent the culmination of decades of technological development, scientific planning, and fortunate timing that have aligned to provide humanity with its best opportunity yet to decode the chemical messages carried by visitors from other worlds. As autumn progressed in 2025, scientists monitoring 3I at LS through NASA's Swift Observatory began to notice something both expected and melancholy. The ultraviolet signal that had first revealed the comet's impossible water outgassing was gradually growing fainter, not because the cosmic visitor had stopped its relentless spraying of ancient molecules into space, but because the vast distances of its hyperbolic trajectory were slowly carrying it beyond the reach of even our most sensitive instruments. The fading of 3I at LS from Swift's detection capabilities marked more than just the end of an observation campaign. It represented a profound moment of transition in our relationship with this interstellar messenger. For months, humanity had maintained an active dialogue with a visitor from another star system, reading the chemical stories written in its ultraviolet emissions and learning about stellar environments that existed billions of years before our world was born. Now that conversation was slowly falling silent as cosmic distances reasserted their dominion. The physics of this fading process reflects the fundamental challenges of interstellar communication. Light, even the high-energy ultraviolet photons that carry hydroxyl signatures, follows the inverse square law with merciless precision. Double the distance, and the signal strength decreases by a factor of 4. As 3I at LS receded from both the Sun and Earth, the twin effects of reduced activity and increased distance combined to dim its chemical transmissions below the threshold of detectability. But the fading wasn't uniform across all wavelengths and observation techniques. While Swift's ultraviolet instruments gradually lost their ability to detect hydroxyl radicals, infrared telescopes continued tracking the comet's thermal emissions for weeks longer. Radio telescopes attempted to detect molecular line emissions that might persist even after optical signals disappeared. Each instrument type provided a different window into the comet's fading presence, extending the observation period as far as physics and technology would allow. The scientific value of these final observations was immense. As 3I at LS faded from view, it provided insights into how interstellar objects transition from active to dormant states. The gradual decrease in water outgassing revealed details about the comet's internal thermal structure and the mechanisms that sustained its impossible activity levels. Scientists could track how different regions of the nucleus responded to decreasing solar heating, mapping the thermal architecture that had enabled such extraordinary behavior. The fading process also revealed something unexpected about 3I at LS's structural integrity. Rather than showing the gradual, uniform decrease in activity that characterizes typical comets as they recede from the Sun, 3I at LS displayed episodic variations that suggested ongoing structural changes. Some regions of the nucleus appeared to shut down abruptly, while others maintained activity longer than thermal models predicted. This irregular fading pattern provided evidence for the complex internal structure that had enabled the comet's unusual behavior throughout its solar system passage. The final Swift observations captured something that will be analyzed for years to come: the isotopic ratios in the last detectable water emissions. As 3I at LS's outgassing decreased, The remaining activity became increasingly concentrated in the most volatile regions of its structure. These final emissions might represent the purest samples of the comet's original composition, uncontaminated by thermal processing or surface effects that could have altered earlier measurements. The emotional impact of watching 3I at LS fade from detectability resonated throughout the scientific community. Researchers who had spent months analyzing its chemical signatures and developing new theories to explain its behavior found themselves witnessing the end of an unprecedented scientific opportunity. The realization that no current or planned missions could follow 3I at LS into deep space added poignancy to its disappearance. This might be humanity's only detailed study of this particular messenger from another star system. But the fading of 3I at LS from direct observation didn't end its scientific contribution. The wealth of data collected during its active phase will support research for decades. Each spectroscopic measurement, each thermal observation, each gravitational analysis contains information that will be extracted and reanalyzed as new theoretical models and analytical techniques become available. The comet's legacy lies not just in what it revealed during its brief period of visibility, but in the questions it raised and the research directions it opened. The infrared observations that continued after Swift lost contact revealed fascinating details about 3I at LS's thermal evolution. As the comet receded from the Sun, its surface temperature dropped predictably, but internal temperatures remained elevated longer than expected. This thermal lag provided evidence for internal heating mechanisms that operated independently of solar radiation, possibly radioactive decay, structural friction, or chemical reactions that continued even as external conditions became increasingly frigid. Ground-based radio telescopes maintained detection capabilities longer than optical instruments, searching for molecular line emissions that could reveal continuing chemical activity even after visible outgassing ceased. These radio observations detected faint signals from carbon monoxide, water vapor, and other molecules for weeks after optical telescopes could no longer resolve the comet's coma. The radio data provided insights into how interstellar objects maintain chemical activity in the deep cold between stellar systems. The final radio detections of 3I at LS occurred in late November 2025, when the comet was already beyond the orbit of Jupiter and receding rapidly toward interstellar space. These last faint signals represented the most distant chemical analysis of an interstellar object ever achieved, pushing the boundaries of what's possible with current technology. The radio signatures suggested that some level of chemical activity might continue even during 3I at LS's return journey to the space between stars. As 3I at LS faded beyond detection, scientists began the complex process of synthesizing months of observations into a comprehensive understanding of what they had witnessed. The data integration revealed patterns and relationships that weren't apparent in individual measurements. The combination of Swift's ultraviolet spectra, Mars orbiter's plasma measurements, infrared thermal mapping, and radiomolecular detections created a multi-dimensional portrait of an active interstellar object, unlike anything previously imagined. The synthesis process revealed that 3I at LS had been even more active and chemically complex than initial observations suggested. The various detection methods had captured different aspects of a sophisticated chemical system that operated through multiple mechanisms simultaneously. Water outgassing was just the most obvious manifestation of internal processes that included thermal regulation, plasma generation, and molecular processing on scales that challenged existing theoretical frameworks. The fading echo of 3I at LS also prompted reflection on the ephemeral nature of interstellar encounters. These cosmic visitors provide brief windows into the chemistry and physics of distant stellar systems, but the opportunities last only months or years before the objects disappear back into the vastness of space. The finite nature of these encounters adds urgency to interstellar object research and highlights the importance of being prepared to maximize scientific return from unexpected discoveries. The legacy of 3I at LS's fading will influence the development of future observation strategies and instrument capabilities. The success of multi-wavelength, multi-platform observations during its passage demonstrated the value of coordinated international efforts to study interstellar visitors. Future missions will be designed with interstellar object encounters in mind, ensuring that humanity is better prepared for the next messenger from another star system. As the last faint signals from 3I at LS disappeared into the cosmic background noise, they carried with them the end of direct communication with a chemical library that had traveled the galaxy for billions of years. But the echo of that communication, preserved in terabytes of data, spectroscopic measurements and theoretical insights, continues to resonate through the scientific community. The fading of 3I at LS from our instruments marks not an ending but a transformation from active dialogue to lasting legacy. The ultraviolet echo that first announced 3I at LS's impossible behavior has now fallen silent, but the questions it raised and the discoveries it enabled continue to reshape our understanding of how chemistry travels between the stars. In fading from view, this interstellar messenger has left behind something far more enduring than its physical presence, a new appreciation for the complexity, diversity and interconnectedness of the cosmic environment we inhabit. The departure of 3I at LS from our observational reach marks more than just the end of a remarkable scientific encounter. It signals the beginning of a fundamental revolution in how we understand planetary formation, stellar evolution, and the chemical architecture of the galaxy itself. The impossible behaviors exhibited by this interstellar visitor have shattered established models with such thoroughness that scientists are now questioning decades of theoretical framework that once seemed unshakable. The traditional narrative of planetary formation followed a comforting pattern of predictability. Stars form from collapsing molecular clouds, planetary disks emerge from the remaining material, and various objects, planets, asteroids, comets, condense at specific distances according to temperature gradients and chemical stability zones. This process, refined through observations of thousands of objects in our solar system, created models that seemed universally applicable to stellar systems throughout the galaxy. 3I has demolished this universal assumption with the casual indifference of a cosmic wrecking ball. Its chemical composition, internal structure, and behavioral patterns don't match anything produced by the planetary formation processes that created our local stellar neighborhood. Instead, it represents evidence for formation mechanisms and evolutionary pathways that simply don't exist in our solar system, forcing scientists to acknowledge that the universe is far more creative and diverse than Earth-based models ever predicted. The water outgassing that initially captured scientific attention represents just the tip of an intellectual iceberg that extends deep into fundamental questions about how matter organizes itself in space. The isotopic ratios found in 3I at LS water suggest nucleosynthesis processes in its birth star that differed significantly from those in our Sun. This implies stellar masses, metallicities, and evolutionary histories that created chemical environments unlike anything in our local galactic region. The deuterium to hydrogen ratios alone tell a story of stellar evolution that challenges existing models of how water forms in different galactic environments. The specific values detected in 3I at LS suggest formation around a star with different mass and chemical composition than our Sun, possibly during an earlier epoch of galactic evolution, when stellar populations had different characteristics. This ancient water carries the chemical fingerprints of stellar processes that may no longer occur in the current galactic environment, but the revolutionary implications extend far beyond just chemical composition. The internal structure of 3I at LS, its low density, high activity levels, and distributed outgassing patterns, suggests formation mechanisms that don't operate in our solar system. The rubble pile architecture, with its network of internal voids and loosely aggregated fragments, might result from gravitational environments, tidal forces, or accretion processes that are characteristic of different stellar system geometries. The sustained activity levels that 3I at LS maintained at impossible distances from the Sun indicate internal heating mechanisms that don't exist in solar system objects. Whether driven by radioactive decay, structural friction, or exotic chemical reactions, these heating sources suggest compositional or architectural features that emerged from formation conditions outside the range of local planetary development processes. The discovery forces a complete reconceptualization of how stellar systems work. Rather than assuming that all planetary formation follows solar system templates, scientists must now consider that each stellar environment creates unique conditions that produce objects with fundamentally different characteristics. The mass of the central star, the metallicity of the initial nebula, the presence of binary companions, the local radiation environment, and dozens of other variables combine to create formation conditions that can vary dramatically between stellar systems. This variability has profound implications for how we understand the distribution of potentially habitable environments throughout the galaxy. If stellar systems can produce objects as diverse as Oumuamua, Borisov, and 3I at LS, then the range of possible planetary environments, atmospheric compositions, and chemical conditions might be far broader than previously imagined. The ingredients for life might not just be widespread, they might be packaged and processed in ways that create habitable conditions under circumstances that current models don't even consider. The chemical processing that occurs during interstellar journeys adds another layer of complexity to galactic evolution models. 3I at LS appears to have remained chemically active during its billion-year journey through space, possibly creating new molecular species and altering its composition through ongoing internal reactions. This suggests that interstellar objects aren't just passive carriers of material between stellar systems, they're active chemical laboratories that continue evolving the ingredients for planetary formation during their cosmic wanderings. The implications cascade through multiple scales of cosmic organization. If individual interstellar objects can maintain chemical activity for billions of years, then the space between stars contains an active, evolving network of chemistry that continuously processes and redistributes the raw materials for planetary formation. This interstellar chemical network could influence the composition of newly forming stellar systems, creating a galactic-scale feedback mechanism that connects the chemical evolution of different stellar regions. The energy sources that drive 3I at LS's sustained activity also challenge models of how energy is distributed and utilized in cosmic environments. The internal heating mechanisms that enable water outgassing at impossible distances suggest energy storage and release systems that operate on geological timescales with efficiencies that surpass anything observed in our solar system. Understanding these mechanisms could revolutionize approaches to energy utilization and storage in both natural and artificial systems. The structural properties of 3I at LS, its low density, internal void spaces, and distributed activity regions, represent architectural solutions to cosmic engineering problems that don't arise in our local stellar environment. The gravitational aggregation processes that created such structures might be common in stellar systems with different mass distributions, orbital dynamics, or tidal environments than characterize our solar system. The revolution extends to astrobiology and the search for life beyond Earth. 3I at LS demonstrates that complex chemistry can remain active and evolving even in the apparent sterility of interstellar space. If life's building blocks can survive and even continue developing during billion-year journeys between stars, then the possibilities for life distribution and evolution throughout the galaxy become far more extensive and interconnected than any Earth-based models suggested. The timing of interstellar object discoveries also challenges assumptions about galactic structure and dynamics. The detection of 3 confirmed interstellar visitors within a decade suggests that our solar system occupies a region of enhanced interstellar object density, possibly related to our position within the galactic disk, or our proximity to stellar formation regions. This local enhancement might influence planetary formation, chemical evolution, and even biological development in ways that aren't apparent from studying only objects native to our stellar system. The technological implications of understanding 3I at LS's energy systems and structural architecture could influence future space exploration and resource utilization strategies. Objects that can maintain chemical activity across interstellar distances using internal energy sources represent natural laboratories for studying energy storage, thermal regulation, and materials science under extreme conditions that can't be replicated in terrestrial environments. The educational and philosophical impacts are equally profound. 3I at LS forces humanity to acknowledge that our solar system represents just one example of how stellar systems can organize matter and energy. The diversity exhibited by interstellar visitors reveals that the universe is far more creative, far more varied, and far more surprising than any models based on local observations could predict. As scientists continue analyzing the wealth of data collected during 3I at LS's passage, each new insight contributes to the growing revolution in cosmic evolution theory. The impossible behaviors that initially seemed like experimental errors or theoretical violations are now recognized as windows into the true complexity and diversity of galactic chemical and physical processes. 3I at LS isn't just rewriting textbooks, it's rewriting our entire conception of how the universe works, how matter evolves, and how the chemical foundations of life are distributed throughout cosmic history. The revolution it has triggered will influence scientific research for decades to come, opening new frontiers of exploration and understanding that would have remained invisible without this extraordinary messenger from another star system. In the end, 3I at LS delivered something far more profound than water molecules streaming into space at impossible rates. It delivered a message, a communication from the deep structure of galactic chemistry that has fundamentally altered humanity's understanding of our place in the cosmic community. This ancient traveler, carrying chemical signatures from a stellar system that predates our world by billions of years, has taught us that we are not alone in a universe of random chemistry, but participants in a vast, interconnected network of molecular communication that spans the galaxy. The message isn't written in radio signals or mathematical patterns, but in the universal language of atomic structure and chemical bonding. Every water molecule that 3I at LS sprayed into our solar system carried information encoded in isotopic ratios, molecular geometries, and energy states that reflect the stellar environment where it formed. These chemical signatures are as specific and informative as any artificial communication system, revealing details about stellar masses, fusion processes, thermal histories, and chemical evolution that occurred in a distant corner of the galaxy when the universe was young. Dennis Bode's poetic description of reading a note from another planetary system captures the profound reality of what interstellar chemistry represents. But 3I at LS has shown us that we're not just receiving isolated messages from individual stellar systems, we're eavesdropping on a galactic conversation that has been ongoing for billions of years, written in the chemical vocabulary of water, carbon dioxide, complex organics, and exotic ices that travel between the stars. The content of this message is revolutionary. The ingredients for life's chemistry are not rare, precious, or dependent on highly specific conditions. Instead, they appear to be natural products of cosmic evolution, emerging wherever the right combination of stellar nuclear synthesis, thermal processing, and chemical self-organization come together. The universe isn't just capable of producing life's building blocks, it seems actively inclined toward their formation, preservation, and distribution across galactic distances and geological timescales. 3I at LS's sustained chemical activity during its interstellar journey suggests that these molecular building blocks don't remain static during their cosmic travels. Instead, they continue evolving, reacting, and potentially increasing in complexity even in the apparent sterility of deep space. This ongoing chemistry means that each interstellar visitor isn't just delivering ancient materials from its birth system, it's bringing the products of billions of years of slow chemical evolution that occurred during its journey between the stars. The implications transform how we think about the origin and distribution of life throughout the galaxy. Rather than requiring each stellar system to independently develop the complex chemistry necessary for life, interstellar visitors like 3I at LS could serve as chemical seed banks, delivering preformed organic molecules and sophisticated chemistry to emerging planetary systems. This interstellar seeding mechanism could accelerate the development of life throughout the galaxy, creating a connected web of chemical evolution that makes biology more probable and more diverse than any Earth-centric model predicted. The message from 3I at LS also reveals the remarkable robustness of life's chemistry. Water, organic compounds, and complex molecular systems can survive billion-year journeys through environments that include cosmic radiation, extreme cold, vacuum conditions, and gravitational stresses that would destroy most terrestrial materials. Yet these molecules not only survive, they remain chemically active, capable of participating in the complex reactions that characterize living systems. This chemical robustness suggests that life's ingredients are far more resilient and widespread throughout the universe than we previously imagined. If complex chemistry can maintain its integrity, and even continue evolving during interstellar journeys, then the barriers to life's emergence and distribution become significantly lower. Every stellar system becomes a potential recipient of chemical gifts from distant worlds, creating opportunities for life to emerge under conditions and timescales that wouldn't be possible through local chemistry alone. The timing of 3I at LS's message is particularly significant. We're living in the first generation of humans capable of reading these chemical communications from deep space. Just decades ago, interstellar visitors would have passed through our solar system completely unnoticed, their molecular messages undetected and unanalyzed. Now, we possess the technological sophistication to not only detect these objects but decode the chemical stories they carry from distant worlds. This technological capability arrives at a moment when humanity is beginning to seriously consider its future as a spacefaring civilization. The message from 3I at LS provides crucial information about what we might encounter as we venture beyond our solar system. The interstellar medium isn't empty space, filled with occasional chunks of ice and rock. It's a dynamic, chemically active environment, where complex molecular processing continues even in the absence of stars and planets. The diversity revealed by 3I at LS and its interstellar predecessors suggests that every journey into deep space will encounter chemical environments and molecular systems that don't exist in our local stellar neighborhood. Each interstellar region might contain unique chemistry, reflecting the stellar evolution, chemical processing, and environmental conditions that characterize different galactic regions. Future interstellar exploration will involve not just reaching distant stars but navigating through chemically diverse environments that could provide both resources and challenges for human expansion. The message also carries profound philosophical implications about humanity's relationship with the cosmos. We are not isolated observers studying a distant universe from our terrestrial perspective. We are embedded participants in a galactic chemical network that has been operating since the early universe. The water in our bodies, the carbon in our cells, and the oxygen we breathe are products of stellar nucleosynthesis that occurred throughout galactic history. 3I at LS reminds us that we are literally made of star stuff that has been traveling the galaxy for billions of years. But the most profound aspect of 3I at LS's message might be what it suggests about the future of life and intelligence in the universe. If complex chemistry can maintain itself and continue evolving during interstellar journeys, then life itself might be capable of spreading between stellar systems through mechanisms that don't require advanced technology or conscious intervention. The same processes that allow 3I at LS to remain chemically active across interstellar distances could potentially preserve and transport living systems between worlds. This possibility extends the concept of panspermia, the hypothesis that life spreads throughout the universe through natural processes, beyond simple microbial survival to include complex chemical systems and potentially even multicellular organisms. The robust chemistry demonstrated by 3I at LS suggests that life's ingredients, and possibly life itself, could be far more mobile and resilient than previously imagined. The message from 3I at LS continues to unfold as scientists analyze the wealth of data collected during its passage through our solar system. Each new analysis reveals additional layers of chemical information that deepen our understanding of galactic evolution, stellar chemistry, and the mechanisms that distribute life's building blocks throughout cosmic history. The full content of this message will take years or decades to decode completely, but the fundamental revelation is already clear. We live in a chemically connected universe where the molecular foundations of life are continuously exchanged between stellar systems through the wanderings of interstellar visitors. The message from deep space that 3I at LS delivered isn't just a scientific discovery, it's a profound realization that life's chemistry is a galactic phenomenon that connects all stellar systems in an ongoing conversation written in the universal language of molecular structure. As 3I at LS fades beyond the reach of our instruments and begins its journey back to interstellar space, it carries with it a new message, chemical signatures of its encounter with our solar system, that will inform whatever stellar region it visits next about the chemistry and conditions that exist around our sun. In this sense, every interstellar visitor both delivers and receives messages, creating a continuous exchange of chemical information that connects the entire galaxy in a vast network of molecular communication. The message from deep space that 3I at LS delivered to humanity is just one transmission in this galactic conversation, but it has been enough to revolutionize our understanding of our place in the cosmic community and the chemical connections that bind all worlds together across the vastness of space and time.